Good day, everyone. My name is Saya. I'm an Australian Research Council DECRA Fellow at the Swinburne University of Technology, Melbourne, Australia. Today, I'm delighted to share one of our recent work, which is using phase change materials with additive manufacturing for thermal storage enhancement in buildings. So, as we all aware, the building sector is responsible for a huge amount of energy consumption. A recent report released by IPCC mentions that about 40% of primary energy consumption and 1/3 of greenhouse gas emissions are caused by the buildings. So this is significant, and various strategies have been recently investigated to minimize the building energy consumption. Some of the strategies involve demand side management, whereas other strategies are with the supply side management. So among the various demand side management strategies, thermal storage and thermal insulation have been widely explored. The main difference between thermal insulation and storage is that the insulation delays the transmission of heat through the building element, whereas energy storage stores the excess or surplus energy and release it when there's a need for energy. So essentially, insulation can only delay the transmission. However, eventually the all heat has to transfer into the indoor, whereas energy storage can prevent the heat transmission into the indoor by storing them. And also it only releases when there's a need for an energy. Thermal storage can be in the form of sensible heat storage or latent heat storage. The sensible heat storage stores the energy by increasing the temperature of the medium, whereas latent heat storage occurs at approximately constant temperature by changing the phase of the material with the so-called phase change materials or PCM. So here we demonstrate the main difference between a sensible storage medium and latent heat storage medium. The one on the right is a sensible heat storage medium with the representation of brick wall, and on the left, this is a PCM layer which represents the latent heat storage. So as the solar irradiance falls on both surfaces, initially both mediums will store the energy by increasing the temperature as sensible heat storage, and the brick medium will continuously increase the temperature as the storage occurs because of the sensible heat storage. However, the PCM layer will now store the energy as latent heat by changing its phase from solid to liquid. And once a material is completely melted as liquid, then the medium will store the energy by sensible heat storage. So compared to a sensible heat storage medium, the latent heat storage medium has a huge amount of energy capacity, and also the energy storage occurs at a constant temperature, which is called the phase change temperature. So if we choose a material that changes its phase at ambient temperature or occupant comfort temperature, we can ensure that the building remains at occupant comfort temperature for a prolonged period, because this transition, the latent heat transition, require a long time in a day. So this is the main advantage of the PCM in buildings. And if the PCM has so many advantages in buildings, what are the limitations or barriers preventing its industrial or commercial applications? Well, the main limitation is that the PCM leakage and incompatibility. So the PCM stores energy by changing from solid to liquid, and the liquid state becomes unstable in most of the cases and causes the leakage, leading to disappear the PCM in a short period of time. And also with particularly with construction materials such as concrete and bricks, there are incompatibility issues involved with the PCM and cementitious material. So we propose a method of overcoming these limitations by incorporating additive manufacturing of building elements, such that PCM leakage and incompatibility issues are prevented. The methodology involved in this work is that we use additive manufacturing for constructing hollow core building elements. The hollow core building elements are constructed as has different filaments consisting the hollow core, and the PCM is incorporated into the hollow space of the hollow core panels. And then we assess the performance of these hollow core PCM panels by using prototype experimental test rooms, as well as conducting numerical study on full-scale building simulations. So this is the additive manufacturing facility at Swinburne University in Australia. So this 3D concrete 3D printer, which is used for additive manufacturing of concrete, can construct up to 6 meter by 3 meter room without any labor involvement. So it, as long as we give a digital drawing of the building and concrete supply to this system, it automatically construct the building without any preparation or any formwork. The main advantage of additive manufacturing or concrete 3D printing is that the complex elements can be easily printed without complexity. As you see, some of the complex elements were printed using concrete 3D printer, whereas these cannot be simply constructed using a conventional construction process. So we take advantage of this additive manufacturing process to construct our hollow core filaments, so that PCM can be easily incorporated into the hollow core. So these are the hollow core filament panels we printed using the concrete 3D printer. And what we do here is, once this concrete is hardened, we incorporate the PCM into this hollow core, and then we seal the ends. And in terms of experimental analysis, we initially measure how much is the PCM can be loaded, or how much is the PCM loading capacity. And then we use the experimental test rooms to assess its performance, for example, by measuring the indoor temperature of the test room, and also heat gain to the indoor by using the heat flow measurements. And this shows the 3D printer we used to print the hollow core 3D printing. And this is a prototype experiment used for the analysis of thermal performance. So this test room consists of 5 surfaces as the highly insulated expanded polystyrene panels, and the top surface is made of the test panel. And then we have an IR lamp, which represents the solar irradiance on the surface. And then we monitor the temperature and heat flow measurements of the inner surface and indoor with time as heating and cooling processes involved. So with the comparison, we use 3 different materials for comparison. One is the control panel, which is also called solid core without any hollow core. And then one is hollow core, that represents the hollows as the insulation, and then hollow core with PCM, which is a novel technology we are introducing. With regarding to the numerical study, we used a multi-story office building, and using these PCM incorporated hollow core panels as the building walls and floors. So we take the experimental properties as the input of the simulation and assess the performance to measure the monthly cooling energy savings using energy plus building simulations. So the results of the PCM loading rate and also the thermal storage of the panels are shown in this table. So as we can see in the table, up to roughly 10% by weight of PCM by weight of concrete can be incorporated into the hollow core of the panels, which is very significant. And also it is reflected on the thermal storage of the panels. The hollow core PCM panel showed roughly 17 kilojoule per kilogram of thermal storage compared to the solid core panel of 0.89 kilojoule per kilogram. So this is approximately 16 times enhancement in thermal storage, which is expected to have a significant improvement in indoor thermal conditions. We also did the leakage test by undergoing multiple thermal cycles of the panels, and we have ensured that the PCM losses were very negligible after multiple thermal cycles. And then we did the thermal performance test using the test rooms explained earlier. And here we report the indoor temperature of the test room for different panels. As we can see here, the PCM panel or hollow core PCM panel showed significantly low temperature during the heating and cooling process compared to the control panel shown in the black line, as well as the hollow core panel without PCM on this discontinuous line. So the maximum peak temperature reduction was determined as 4.88 degrees Celsius, which is very significant with the PCM incorporation. Interestingly, we can also see that the hollow core panel without PCM showed comparably high temperature than control panel, and this represents the lack of thermal storage in the hollow core panels. So as we make the panel as hollow core, the core of the element is subtracted, so which loses the sensible heat storage. Even though it acts as an insulation medium, it does not help in reducing the indoor temperature because they are significantly losing its thermal storage, the heat storage, sensible heat storage. Then we compared the inner surface heat gain or indoor heat gain rates for PCM panel as well as the control panels. We can see that the PCM panel has shown comparably low heat gains to the indoor, which is a representation of the reduction in indoor heat transmission. And also we can see the melting heat transformation with PCM. As we see up to certain time, the heat gain rates are mildly increasing, which means PCM is melting. And at the end of the melting, a rapid increase in the heat gain rate can be observed. So this is after complete melting of PCM. Such behavior cannot be observed in solid core or hollow core panel because they don't have a latent heat storage medium. Once again, we can note that the peak reduction in the heat gain rate was reported as 46%. Then we did the building energy simulations to measure monthly cooling energy savings. And as we are in Australia, which is in Southern Hemisphere, December, January, February are the summer months for us. So during these months, for the cool temperate climate zone of Melbourne, we can see that the energy savings of up to 20% can be observed, whereas for warm temperate climate zone, it is reduced for up to 10 to 15%. So in other months, the energy savings has been seen as very high because since they are cooler months, the cooling energy demand is comparably low. So in that conditions, PCM operates very well. However, the need of PCM is only important in summer months, and then we report the energy savings as only for summer months. However, the annual cooling energy savings were also measured or determined, and we have noted that up to 48% of annual energy savings can be observed for this proposed hollow core PCM panel in buildings. So, well, if the proposed methodology is successful in terms of reducing building energy consumption and improving thermal comfort, what are the future directions in this technology? We can propose that additive manufacturing not only enables these hollow core PCM panels, it can also be used to make ventilated slabs and chilled water slabs, where these slabs can be used for air ventilation, as well as chilled water, which is used to cool down the rooms. So additive manufacturing also enables the hollow core construction with the insulation foams instead of PCM in the hollow or in the hole to increase the insulation capacity of the panels. And one of the feasible technology in additive manufacturing is that the facade construction, because concrete facades are very common in Australia, and they are mainly made in precast construction. So it facilitates the use of additive manufacturing or concrete 3D printing for making hollow core facades, which can be manufactured as offsite as precast elements, and then used in the buildings as building facades by incorporating PCM or insulation into the halls. However, we also need to note that the additive manufacturing has its own challenges, and they need to be overcome to make this technology successful. So in summary, we can say that the proposed hollow core with PCM technology has shown a significant enhancement in thermal energy storage by approximately 16 times compared to conventional concrete construction. And by using these hollow core PCM incorporated panels, we can reduce the indoor temperature of the test room by up to 4.88 degrees Celsius with the heat gains reduction of up to 46%. Also, monthly energy savings of up to 20% can be achieved during the summer months. So with that, I would like to conclude my presentation. If you have any questions, I'm happy to answer. And also, if you're interested to collaborate in our work, you can reach me out with the email given here. Thank you very much.